Very good. Okay, so today we'll start with 3E. We'll see how we're going. So we're talking about rational functions, and rational comes from the word ratio, means the function is expressed as a ratio, as a fraction. We have something at the top, a function at the top, and a function at the bottom. Notice that, we've got 3 dot points here, and we learned these in 11 methods, but just to recap, the roots will occur when the function is 0, which is when the top part of the function is 0, okay? So we define that as y is f on g of x in our notes there. The vertical asymptote occurs when the denominator is 0, and a horizontal asymptote may occur. We need to use technology and intuition to discover it, and now a divisibility method as well. Okay, part A says find the asymptotes and discuss behaviour near them. So the first thing we should be looking at is, well, it's got this denominator and it's going to be undefined when the denominator equals 0. And so the denominator x take 5 equals 0, and so we'll get x equals 5. There's an asymptote at x equals 5, and it's a vertical asymptote. I know it's vertical because the definition of it is it's an x value equal to 5. X equals 5 is a vertical line, which would be drawn at the x value of 5. Here's 5, we've got an asymptote there. Every x value on this line is 5. Very good. So that's the first, the vertical asymptote, but we need to discuss the horizontal asymptote. Now there's 2 ways of doing this really. We can just think about what happens as x approaches positive infinity and as x approaches negative infinity. We can sort of put it in there and we can see we'll have 2 infinity divided by infinity. Alright, so 2 infinity is twice as large, so it's going to approach a factor of 2. But let's demonstrate that's true over here by performing this divisibility. And this will pop up later that you have to do this in order to find the equation of the oblique asymptote. More on that in a moment. So I've got 2x plus 3 divided by x take 5. That's the function that we're presented with. Now I'm going to perform that division. So I've got it set up in our division algorithm. Here's 2x plus 3. Here's my x take 5. Alright, so I'm dividing a linear by a linear. There's not much involved in this at all. Remember, the question we ask is, what do I need to multiply x by to get 2x? What do I need to multiply x by to get 2x? And the answer is positive 2. Okay, so I'm going to go 2 multiplied by x will give me 2x, and 2 multiplied by minus 5 gives me minus 10, and I subtract that away, right? 2x take 2x will cancel, and then we have 3 take minus 10 will be positive 13. Alright? Now, this is our remainder, this is our quotient, this is our divisor. So what we have then is we have an alternative way of expressing this function. Alright? Remember, if we have p of x on top of d of x, it's equal to the quotient of x plus the remainder on top of the divisor. Alright, so in our terms over here, we have some polynomial divided by the divisor. It's going to be with the quotient plus the remainder on top of the divisor. Now this is a particularly useful way for us to express it. Alright? This function and this function are equal. Okay, now what's super good about this, alright, I've got 2 plus 13 on top of x will take 5. We can really observe what occurs at the extremities of the function. So let's make the case. As x approaches positive infinity, alright, this part is going to stay as 2, and over here we're going to have 13 divided by infinity. Alright, 13 divided by infinity. This component is approaching 0. 0 from the positive direction, because this is a positive number. So as x approaches infinity, this component, alright, as x approaches infinity, 13 on x take 5 approaches 0 from the positive direction. So we have this part is approaching 0 from the positive direction, which means the y value is going to approach 2, because we have 2 plus 0 from the positive direction. Alright, so it's approaching 2 from the positive direction. And similarly, as x approaches negative infinity, alright, we have 13 divided by a really negative number. It's still going to be approaching 0, but from the negative direction. So that component 0, so we have 2 plus approaching 0 from the negative side. We have y approaching 2 from the negative position. All right, and so that means we have an asymptote at y equals 2. Okay, so we've got x equals 5 here, and our other asymptote, so we have a vertical asymptote x equals 5. Let's answer the question, I suppose. Vertical asymptote x equals 5, and a horizontal asymptote y equals, now asymptote should have one s, sorry, y equals 2. And we can see that here, 2x on top of x, right? Won't always be the case, will for linears, but require investigation with the polynomial division. You can observe that on your graph too. Find the asymptotes and discuss behaviour near them. So what's going on? Like, let's just talk about it, what's going on. As we approach x equals 5 from, we can think about it in 2 ways. As we approach x equals 5 from the positive direction, which way, oh, let me put my other asymptote in as well. Yeah. Okay. So the function is going to be constrained in here and here. Could be here and here, but let me explain my reasoning as to why it's going to be here. We already said as x approaches positive infinity, y approaches 2 from the positive direction. Okay, so we have that approaching 2. This is y equals 2 from the positive direction. Okay, that's the first thing. And then we can think about, okay, what about as x approaches 5? Remember, this is an x value of 5. As x approaches 5 from the positive direction, what we'll have here is we'll have like 5.1 or 5.01 or 5.001. The point is this denominator is positive. Okay? So we have one positive number, we'll have 13, divided by a really, really, really small positive number. The result is still positive. And when you have a number divided by something approaching 0, it skyrockets to infinity. So that's what's going on up here. As it approaches 5 from the positive direction, or from above 5, it approaches positive infinity. And we can make the same case going here. We know that as x approaches negative infinity, it approaches 2 from the negative direction, or from below. And as it approaches 5 from below, so if I put in there 4.9, the denominator is negative, isn't it? And so we have a positive number divided by a negative. It's going to be a negative result, and it's going to get way negative as this gets closer and closer to 0. Okay, really good. So that's the asymptotes. Find the axis intercepts. Okay, so rational function. The x-intercepts occur when the numerator is 0, so 2x plus 3 equals 0. We'll solve for this. Alright, so I have not drawn the x-intercept in the correct spot. Let's put that minus 3 on 2. There we go. And the y, remember when it says axis, that would mean both x and y intercepts. So the y-intercept occurs when x is 0. So I put x is 0 into this equation, I'll have minus 3 on 5. And then graph the function. Alright, so all of those skills, right, we can observe from our graph, but I do want us to get in the habit of thinking about what's going on with these tangents, what's going on with these asymptotes. Now, does that skill seem okay? Would you like to try a few of them before we do the quadratic, or do you just want to get straight into the quadratic on the next page? What do you reckon?
All right, we'll just go quadratic.
Just get on with it? Let's do it. So I'll clear some space and pause for a moment. So we have the function x squared, take 2x, take away 3, on top of x plus 2. Find the asymptotes and discuss their behaviour near them. So what we've got 3 types of asymptotes, right? We've got a vertical asymptote, a horizontal asymptote, and the one we're going to learn about now that we haven't talked about before is called an oblique asymptote. And all that means is it's an asymptote that is diagonal, all right? It's the equation of a line. So, we can observe it on the graph in a moment. And let's talk about the circumstance when this occurs. An oblique asymptote will occur on a rational function when the numerator is 1 degree higher than the denominator. Okay, this is a quadratic, it has a degree of 2. This is a linear, it has a degree of 1. The numerator is 1 degree larger, so we will have an oblique asymptote on this function. Similarly, if we had a cubic divided by a quadratic, okay, the numerator would be 1 degree higher. So oblique asymptote occurs when the numerator is 1 degree higher than the denominator. All right, that's important to note. When numerator is 1 degree higher. And maybe first, even, let's just sketch it first to demonstrate that we do have an oblique asymptote there. So can you pull your calculators out and I'll show you exactly what I mean. So x squared take 2x take 3 divided by x plus 2. And if you set your V window to standard, it doesn't quite pop up with the whole graph. You just need to move down one, press the down arrow, one section. So I'll pop it up here before I make the argument as to what's going on. So it looks something like this. Okay, everyone see that? And so where this oblique asymptote occurs in is this line here. Okay? And it's a diagonal line, right? So it's the equation of a line. And we're going to discover it using the division process. One thing we can do is trace along it and observe a relationship, okay? But I think the best way to find it is to perform this division. So, we have x squared take 2x take 3 divided by x plus 2. Let's perform that division using the division algorithm. You can perform synthetic if you like. So our question, what do I multiply x by to get x squared? The answer will be x. So I'll go x times x gives me x squared. X times 2 gives me 2x. We'll subtract that away. We'll be left with minus 4x and then take away 3. And what do I multiply x by to get minus 4? Minus 4. So I'll perform that. Minus 4 times x. Minus 4 times 2. Subtract that away. Cancel. Minus 3 plus 8, positive 5. So we have our remainder, we have our quotient, we have our divisor. So an alternative way we can express this function is our quotient plus the remainder on top of the divisor. And our quotient here is the equation of our oblique asymptote. Okay? So let's show you that this is true. I want you to sketch 3 functions now. So you've already sketched this one. Okay? In y2, I want you to sketch this function. X take 4 plus 5 on top of x plus 2. And then lastly, I just want you to sketch the line x take 4. So y1, y2, y3. So 2 of them are going to be the same, okay, just demonstrating that they're the same. And then the last one, if we graph x take 4, we can see the asymptote that they approach from both directions. Okay, now let's explain what's going on here as well. Okay, I have it in this form, x take 4 plus 5 on top of x plus 2. Now let's talk about what happens to this component as x approaches positive infinity. As x approaches infinity, we have 5 divided by an enormous number. This part is approaching 0, which means the equation of the line is approaching x take 4, but from the positive direction, because this is 0 from the positive direction. Okay, so that's what's going on there. And then the same in the negative direction. As x approaches negative infinity, this component approaches 0 from the negative direction. So this is going to 0, so it's approaching x take 4 from below. So that's what's going on there. That's the equation of an oblique asymptote. Now, so the question we're asked to do, let's finish answering it. Okay, find the asymptotes and discuss behaviour near them. So asymptote, we've got the vertical, clear some space. We have a vertical asymptote when the denominator is 0. I'll sketch that one on here. Here's our vertical asymptote. So the denominator, x plus 2 is 0. So we have a vertical asymptote at x is minus 2. And then we have an oblique asymptote at y equals x take 4. Alright, so now you can see as well where that division skill comes in handy. Like we learned division for the purposes of observing these characteristics within a polynomial, within a rational function. Okay, so that's part A. Part B, find the axes intercepts. So the y-intercept when x is 0. So that's going to give us minus 3 on 2. Alright, I've got that there. And our x-intercepts, we can g-solve, or you can factorize. These ones are rational. Minus 3 and positive 1. Anyway, our x-intercepts, so we can factorize it to be the numerator I'm talking specifically about. Let's make the case. Okay, roots occur when the numerator is 0. So x squared take 2x take 3 is 0. And if we're factorising this, two numbers multiply together to give us minus 3 and add to be minus 2. So x take 3, x plus 1. And so our solution then applying the null factor law, x is 3 or x is minus 1. So they're the x-intercepts. We've got the y-intercept. We've got the vertical asymptote. We've got the oblique asymptote. And we've got an approximate graph of it here. Now, when you're graphing, okay, in a test or in an exam, having marked exams, students lose easy marks on graphs because they rush them. All right. So I'm going to say, when you're confronted with a graphing question, do it carefully, do it properly. We and SACE will always provide you with a V window, a Cartesian plane. So set your calculator to those same constraints. And one thing you can do is use F1 when you have a function to trace along it, okay? So that it gives you an idea of where a couple of points are. What's even useful is to just plot a few points as you're going. What's it at x equals minus 1.5? What's it at x is minus 1? What's it at x is minus positive 2? And then you've got these points and you know the function has to go through them. When we mark it, okay, generally for a graph you have 3 marks. And we're investigating firstly like features of the graph. So it might be having the maximum and minimum in the correct location. And what that means is you're graphing it on grid, right? And so we, on grid, you know, let's say this is your sort of grid you've got here. And if we're marking it, that let's say the minimum point occurs here, all right? We say it has to be somewhere in these 4 boxes, all right? So it's pretty lenient, all right? But if you're outside of this box or on the edge of that box, you don't gain that mark for getting the minimum or maximum. position. So shape is important when it comes to graphs. Anyway, the Hazy textbook that we're going through only offers these problems. It doesn't give us ones where we find oblique asymptotes. So I'm going to write up a few questions that I'll give to you guys to do as an extension. This is part of the course that is required, but it's not in our textbook, so we do need to go through that. All right, Max.
It says part A, and discuss behaviour near the asymptotes.
Very good.
As x approaches infinity, do
Yep.
you write that the graph approaches x take 4 from the positive direction?
Very good. Yep. And then the opposite for the negative
Yeah.
direction. Yep. Really, really good. So the reason I focused on that component, I mean, this component is going to approach infinity as well, but the point is this part's approaching 0, and so then the y value is approaching, it's approaching x take 4 as x approaches infinity. Yeah, really good. Happy with that? Yeah, cool. All right, so let's try out this exercise. I think you'll find it okay.